Hello everyone, this is part 2 of our video on parametric surfaces, aka parametrized surfaces. And in this particular video, we're going to be talking about in some sense, the reverse of what we did yesterday. Yesterday, someone gave us a formula, a parametrization for a surface, and then we needed to figure out what graph corresponded to that and what normal vector corresponded to that. In this particular video, we will be going backwards. Someone's going to hand us a particular shape, a particular surface. Someone's going to hand us a particular normal vector, and our job is to construct a formula that is consistent with that given information. To get started with that, we're going to talk about the concept of an orientation for a surface. And to set the stage for our talk about orientation, let's go back to the previous video for a minute and remember that when we concluded yesterday's video, we noted that a particular surface had many possible normal vectors at any particular location. For example, if you had a sphere and you were considering the location on the sphere on this right side, then one possible normal vector was outward facing, maybe of a particular length of 1 or something. But if I increased the length of that vector, it would still be normal. It would still form a right angle with the surface. If I decreased the length of that vector, it would still form a right angle with the surface. And if I went in the opposite direction and I went into the sphere, that would still be forming a right angle with the surface as well. Now, if you say, okay, I don't want to consider all those possible lengths, I only want to consider unit vectors, vectors with a length of specifically 1, alrighty, now you're down to only having 2 possible normal vectors. The vector that points in one direction, in this particular example, outside of the sphere, and the vector that points in the opposite direction, the one that points into the sphere. An orientation of a surface is a decision, is a choice about which of these 2 normal vectors you're going to use. For example, I could give the sphere the outward orientation, and that would correspond to choosing this blue vector, this blue normal vector. Or I could choose an inward orientation. I could choose this yellow normal vector. An orientation is a choice of normal vector, inward or outward, upward or downward, etc. Now, what are we doing when we choose an orientation? What are we doing when we choose a normal vector? To do an analogy, let's go back to physics for a minute. And in physics, in order to make sense of things like displacement, velocity, etc., you had to decide at the beginning of the problem what direction was going to correspond to forward, what was going to correspond to the positive direction. What we're doing here when we choose an orientation for a surface is a very similar decision about what is going to be treated as positive and what is going to be treated as negative. It helps me to think about the surface in the problem as being like a filter, like a pool filter. And when we choose an orientation, we're making a decision about what direction of flow through that filter will be treated as positive. Will it be a positive flow if we move out through the sphere, or will it be a positive flow if we move into the sphere? That is what we're doing when we're choosing orientation. We're choosing a positive direction so that all the signs in our calculation are consistent and make sense. Now, in a situation like a sphere, or more generally, if you're dealing with any surface that completely encloses a 3-dimensional region, a sphere, a box slash cube, a donut, any surface that completely encloses a region. When in doubt, unless somebody specifies otherwise, the convention is always to choose the outward orientation. positive flow is out through the surface. Now that we've talked a little bit about orientation and what that word means for a surface, let's talk about how we can come up with a formula, a parametrization for a surface where someone has chosen the orientation already. If an orientation for a surface has already been specified, if someone has already picked their normal vector, then to ensure that all of your calculations have the correct sign, any parameterization for the surface must have the following property. Yesterday we talked about if your parameterization for a surface was denoted by r parentheses u comma v, then the vector ru cross rv was a normal vector to the surface. But in order to make sure that your calculations all have the same sign, your parameterization should have the property that ru cross rv is in the same direction as the normal vector that you chose when you picked an orientation for the surface. To demonstrate what I mean, let's consider the following example. Someone is considering the paraboloid z equals x squared plus y squared, and they want to come up with a function r of uv whose graph corresponds to this paraboloid. They want to parameterize this surface. But they want to do it in such a way that we respect the orientation of this surface. So they say, okay, someone has come to me and they want this surface, they want this paraboloid to be oriented in the upward direction. So for example, at the location 0, 0, 0, at the bottom of this paraboloid, we want the normal vector to point up. Let's see if we can find a parameterization R of uv, which parameterizes this surface and which has the property that Ru cross Rv points upward, for example, at the origin. Now, yesterday we observed a general fact. We observed that if you set x to be u and y to be v, and the z component to be equivalent to the z formula when x is replaced by u and y is replaced by v, then this will parameterize the surface. Now, let's quickly check the orientation that corresponds to this r sub uv to make sure that r sub u cross r sub v truly points upward. Let's begin by finding these partial derivatives. R sub u would be equal to 1, 0, 2u, and r sub v would be equal to 0, 1, 2v. And let's consider a specific point. Let's consider, for example, the location here at the bottom of the paraboloid, the location where x and y and z are all 0, the location where u and v are equal to 0. At this particular location, our partial derivatives become 1, 0, 0 and 0, 1, 0. And therefore the cross product can be calculated relatively easily. You can confirm that the result of that will just be a vector of length 1 in the positive z direction. Now I can confirm that 0, 0, 1 does in fact point up, and therefore it has exactly the same direction as the normal vector that we chose when we said orient upward. Therefore, r of uv equals x equals u, y equals v, and z equals u squared plus v squared would be an acceptable parametrization for this surface with this orientation. Now, what if instead they said, okay, I want to parametrize this paraboloid, but I do not want it to be oriented upward. Instead, I want it to be oriented downward. I want a downward flow through this surface to be treated as positive. In that situation, how could I parametrize the surface to match not only the shape of the graph, but also to match the new parametrization chosen? So our previous idea will no longer work, right? If x is equal to u and y is equal to v, and z is equal to what you get when you replace x by u and y by v, then we found that that particular choice, attempt at parametrization, corresponds to an upward orientation. If I want to get the opposite orientation, here is a reliable trick that you can use. To get the opposite orientation, reverse the roles of u and v. Specifically, what I mean is, instead of letting x be equal to u and y be equal to v, I'm going to let x be equal to v and y be equal to u, so that x squared becomes v squared and y squared becomes u squared. Let's confirm that this choice, where x is v, y is u, and z is equal to x squared plus y squared, becomes v squared plus u squared. Let's confirm that this will have the downward orientation that this particular problem is looking for. If I calculate the partial derivative in the u direction, then I get 0, 1, 2u. If I calculate the partial derivative in the v direction, then I get 1, 0, 2v. Now if I once again consider the location on the paraboloid down here at the bottom, this location that corresponds to a u and an x of 0, 0, then the partial derivatives will become r sub u is equal to 0, 1, 0, and r sub v this time is equal to 1, 0, 0. So if I take the cross product in the order Ru cross Rv, as our formula requires, then the result of the cross product in this case will be 0, 0, and -1, which, truly enough, does point downward, as it should be. And therefore, this formula, where the x is v and the y is u, and the x squared plus y squared becomes v squared plus u squared, this would be the parametrization for this paraboloid with the downward orientation. Let's do one more example. This time, let's try and find a parametrization for this sphere of radius 3. Now, the sphere completely encloses a three-dimensional region. Unlike the paraboloid, which is sort of open at the top, the sphere completely encloses a region, and therefore the standard choice of orientation, the conventional choice of orientation, is outward. So let's try and find a parametrization for this sphere which matches the standard outward orientation. Now, yesterday we saw that a parametrization for the sphere could be found by leveraging the spherical conversion formulas. Last time, a sphere of radius 1 corresponded to the case where the x component was given by sine u sine cosine v, the y component was given by sine u sine v, and the z component was given by cosine of u. But that was for a sphere of radius 1. That was for the case that rho was equal to 1. And that's not what we want here. In this particular case, we want our sphere to have a radius of 3 to match the radius that we are given in this Cartesian equation. So to that end, I'm going to try the following parametrization. I'm going to try one where I multiply by the radius of rho equals 3 in each component. So now, let us check whether this parametrization corresponds to an outwardly oriented sphere. Yesterday we saw that if we consider the location where u was equal to pi over 2 and v was equal to 0, then that corresponded to this location on the front of the sphere. Now, for an outwardly oriented sphere, the normal vector to the sphere at that location should also point in the positive x direction. So let's check whether or not our parametrization that we've constructed truly satisfies that property. Let me start by finding the partial derivatives in the u and in the v directions. The partial derivative with respect to u will be equal to 3 cosine u cosine v in the x direction will be equal to 3 cosine u sine v in the y direction, and will be equal to negative 3 sine u in the z direction. The partial derivative with respect to v will be equal to, it looks like, negative 3 sine u, and that cosine v in the back will become sine v. If I take the partial derivative of the y component, it looks like it'll become 3 sine u cosine v. And because the z component has no v's in it, the z component will just zero out when you take its partial derivative. Now, if I restrict my attention to this specific test location, pi half 0, that I am using, then the partial derivative in the u direction will become, it looks like, 0 from cosine of u, 0 again from cosine of u, and negative 3. R sub v at that test location will become, it looks like, 0 from that sine of v, 3, and 0 again. So now let's load them into a cross product and check and see if we get the correct normal vector. Put them in order. So the result of that looks like it will be equal to 0, take away 9, positive 9, 0, and 0, which is indeed pointing outward from the sphere at this location. It is indeed pointing in the positive x direction. So this parametrization that we have just found, this parametrization where the x is equal to 3 times sine u times cosine v, where the y is equal to 3 times sine u times sine of v, and z is equal to 3 times cosine of u, would be a parametrization for this surface that has the correct outward orientation. Now, someone says, actually, I want my sphere to have the inward orientation instead. I want to fly in the face of convention, and I want an inward flow into this sphere to be treated as positive. If you're in that situation, if you want to reverse the orientation of your parametrization, then all you have to do is steal the formula that you got before. So I've done a bit of stealing here. I've copy pasted our answer from the previous part. And all I'm going to do now is I'm going to go into this formula and I'm going to reverse the position of u and v. And by reversing u and v in our formula, then just like last time, that will succeed in reversing the orientation as well. So this is the parametrization that I would use for a sphere of radius 3 oriented inward. That concludes today's material. We talked about how to check whether a particular parametrization was a match to the orientation chosen for a surface. If the parametrization and the orientation are mismatched, then that can be fixed very easily by simply flipping and exchanging u with v. If you change the position of u and v in the formula, if you completely swap them, then that will have the effect of causing the normal vector to swap direction as well. Which surfaces should you be able to parameterize? I am expecting you to be able to parameterize spheres of various radii using these spherical conversion formulas, just as we did in this example. I am also expecting you to be able to parameterize surfaces that come from graphing equations of the form z equals some function of x and y, because functions of this format can be parameterized very easily by just setting x to be equal to u and y to be equal to v, or vice versa. That concludes today's material. We will be using parametrized surfaces in the next several days of lecture to figure out surface integrals.